First, congratulations. You made it to the end. This is the last lecture in this first part of 600, and we're delighted that you've stuck with us all the way along. Second, this is going to be a short lecture because we just want to take a step back and think about what have you accomplished, or what have we, hopefully together, accomplished in this course. So, to pull all of this together, let's think about where you've been and where you're headed. What are the things you've learned? What are the lessons you should take away? And how might you use this as you think about next steps? And let's start with where you've been. If you go way back to the very first lecture, we put up a set of topics. We said in this class, in this course, you're going to learn a different range of information, a different set of knowledge, a different set of tools. And if you think about it, I think we've hit all of them. You've certainly learned about how to represent knowledge with different kinds of data structures. Lists, tuples, dictionaries. They aren't the only ones. As you move on, you'll find other kinds of data structures, but most importantly, you've learned the idea of how to group things together, treat them as primitives, so that you can reason about complicated structures in very efficient ways. Second thing we certainly did was to come up with different computational metaphors, iteration and recursion. You've seen loops, whether it's for or while loops. You've seen ways of writing things that walk linearly through different kinds of computations. You've seen recursion as a way of capturing computation very effectively. And they really are that wonderful term over there. They're metaphors for thinking about how to write procedures that tackle problems. You've certainly seen the idea of abstraction, both of data types and of procedures. That notion that I can create something once and then bury the details so that I can use, for example, a procedure as if it was provided as part of the machine. Knowing that, having built it once, there's a contract that ensures if I give it the right kind of input, I'm going to get out output that satisfies a particular constraint. You've definitely seen how to organize and modularize systems, especially around the ideas of using object classes and methods, associating both data and procedures together inside of classes, treating them as primitives, building hierarchies, inheriting, all tools that are really valuable for organizing and modularizing your systems. You've also seen different classes of algorithms, both for straightforward things, but especially around things like searching and sorting, things that you do a lot, and associated with that, you saw how to reason about the complexity of different algorithms. Why do certain things have much more cost than others? What's the order of growth associated with inherent kinds of methods and algorithms? So those are all the topics that you covered. If you also think back to that first lecture, we also said that we were going to teach you some higher level things. You were going to learn computational modes of thinking. We want to master the art of computational problem solving. And especially, we said, we want to help you have the confidence to make computers do what you want them to do. So what we hope is, in fact, that we started you down the path to being able to think and act like a computer scientist. That when you see a problem, you think about how can I abstract that? How can I build the right kinds of modules? What are the interfaces between those modules? How do I approach this computationally? And what does that allow me to do in terms of solving a problem, especially to get the computer to do the hard work for us? So if we hope we started you down the path of thinking like a computer scientist, you might ask, well, what do computer scientists actually do? And I happen to put up here images of two of the earliest computer scientists and two of my favorite ones. Ada Lovelace, sometimes referred to as the first computer programmer, and Alan Turing. And what do they and more recent computer scientists really do? Well, they do think computationally. Abstractions, algorithms, automated execution. Three tools that you've seen and that we're going to summarize in a second. And in particular, just like the traditional 3 R's of reading, writing, and arithmetic, computational thinking is becoming a fundamental skill that every well-educated person is going to need. And so that ability to think about abstractions, to think about algorithms, to think about automated execution is a tool that's as valuable as being able to read, write, communicate, and do other kinds of basic computational things. So, what is that notion of computational thinking that we hope you've learned? Well, here are basically the steps that you've seen. Given a problem, how do I identify or invent useful abstractions? How do I suppress details that I don't need to worry about? What are the interfaces between the pieces that I want? Once I've done that, how can I formulate a solution to a problem as a computational experiment using those abstractions? What is it I want to test? And then having done that formulation, how do I design and construct a sufficiently efficient implementation of the experiment? Sufficiently efficient, a key word, because we know that some things have more cost than others. Having done that, then I'm going to validate my experimental setup. In other words, debug it to make sure it works the way I want it, run the experiment, evaluate the results, and repeat as needed. That really is the tools that hopefully you're taking away here as you think about what does it mean to run a computational experiment. And then what are the components of that? Well, the 3 A's of computational thinking. Abstraction. You've seen many examples of this. How do I choose the right abstraction? How do I operate in multiple layers of abstraction simultaneously? You saw a lot of this when we played with classes, but it shows up in other places as well. How do I define the relationships between the abstraction layers? But abstraction is an essential part of computational thinking. I don't want to have to think about hundreds of thousands of lines of code at a time. I want to be able to take a piece, make sure it works well, understand the constraints on it, and abstract it away so I can just use it as if it was a built-in thing around it. I want to be able to understand where's the right level in that hierarchy of abstractions in which to be performing my work. And you've seen examples of that. You're going to see a lot more of them as you use computation moving forward. Abstraction, a big element of all of this. Automation, second big element. How do I think in terms of mechanizing those abstractions? It's not just enough to think about what's the algorithm. How do I do it in a way where I can write it down so that the machine can actually understand it? And that mechanization is possible because we have precise and exact notations and models. And because, as we saw way back at the beginning of the class, there is some machine that can interpret that notation. And so learning a new language, in fact, is learning what's the description of the mechanisms and how do I map things from my thinking level of abstraction down into something that the computer can actually do. And then algorithms. How do I then take those ideas and capture common patterns of behavior that I want to use? And that includes both what language do I use for describing the automated process? In our case, it was Python, maybe something else in the future. But it also allows me to abstract away the details of the algorithm. Having built the algorithm once, I can extract away the details so I don't worry about it. And finally, how do I use algorithms actually as a language for communication? Talking about an algorithm at a high level is a way of actually communicating a process or an idea to somebody else. If you look back at everything you've done in this class, you'll see those 3 pieces constantly. Abstraction, automation, algorithms. Those are the 3 A's of computational thinking that you're going to take forward. The last aspect of this is to think about computational thinking at a slightly higher level. And here, there are 2 other things that you've taken away, we hope, from this class. The first one is when given a new problem, how difficult is it? How best can I solve it? We know that theoretical computer science gives precise meanings to these and related questions, and you've seen that. Knowing the difference between a log linear algorithm and an exponential algorithm is really important. Realizing that a choice in algorithm can move you from a more costly class to a less costly class is really valuable. Also knowing that some algorithms inherently belong in this really expensive class is a valuable lesson to take away. But you ought to, when confronted with a new problem, ask, how difficult is this? Does it fit into a class I've seen before? Is there an existing algorithm that's going to solve this problem for me with some small variations? And how do I use that? And then the last aspect of computational thinking we hope you've taken away from this is how to think recursively. It's that wonderfully twisted way of thinking, but it is an incredibly valuable one. And that is that idea of taking what seems like a difficult problem and reformulating it into a simpler version of the same problem, plus some other things that I know how to do. That reduction, embedding, transformation, simulation idea is really valuable, but it all relies on that nice notion of, given a complex problem, I don't have to start from scratch. I can simply say, I could solve this by solving a simpler version of the same problem, and then taking that solution, add in some other things I know how to do in order to make it work. And while it may seem twisted, that idea of recursion really does show out nicely. And this image called the Drost effect wonderfully captures it, based on a Dutch cocoa company's ad. But you get the idea that when I have a recursive problem, I can keep reducing it to simpler and simpler versions until eventually, somewhere way down in here, I get to a base case and I can pull it all together to come up with the solution. I hope this image really captures for you that idea of taking a complex problem is not so hard when you simply reduce it recursively to simpler versions. And those are the things that you've seen. So, that's where you've been. Where are you headed? Well, that's your choice, of course. But I hope that you'll take away two things as you think about how to use what you've seen in this class. How can you use it? And what are next steps to enhancing your knowledge? In terms of how you can use it, well, you should look, I hope, for ways to apply what you've learned. Can you use algorithmic approaches in your professional life? No matter what you do, there's got to be some place where abstraction or computational experiments can improve what you do in your job. If you're a student, ask how you can use these ideas to help you pursue your choice of discipline more effectively. You don't have to be a computer scientist to use computational thinking. An economist, a statistician, a chemist, a physicist, a biologist, mechanical engineer, they all use computation in different ways. And I really encourage you to think about how you can use algorithmic approaches to solve problems in your own domain or discipline. You can ask the same question about your personal life. Can you organize your personal finance records better? As we saw in the last lecture, can you plan your retirement better? Can you store your historical records better? Can you simply use computation to help you in things that matter to you in personal life as well as professional life? So I hope you'll think about how can you use what you've learned here in multiple ways. And the other next step is basically to think about taking another course in computation. As we said, the next course in this sequence, the second part of 600, is an introduction to computational thinking and data science, where we look at using these tools in large-scale data analysis. But you might take a course in algorithm design, in software engineering, machine learning, a very important and hot topic, in data analytics and data storage, and whatever tickles your fancy. Basically, you've got an opportunity to build as you see fit because you've learned the basics of computational thinking and algorithmic processing. So, good luck. However you choose to use computational thinking, we hope that it's a useful tool for you in many ways. As a way of approaching professional problems, as a basis for understanding the impact of computation in everyday life, and as a language for communicating ideas. And I look forward to seeing you do that as you take more courses and you add computational thinking to your own professional and personal life. Good luck.